the neutrino spectrum is here. As you can see, it's well below the GZK, the ice cube limits. Well, actually, our spectral shape is different than the spectral shape that ice cube used. So in order to be more compatible with the ice cube limit, we calculated what's the area under the neutrino flux, and we rearranged it as if it were a broken parallel, which is like this, and then that's the thing. So these are even with forcing a Waxman-Bacall type of spectrum, we're below the ice cube limits in these time-dependent calculations. We also have a cosmogenic GZK neutrino contribution. That's from the propagation through, from redshift 6 down to the present. But these are, of course, cosmic rays from within the GZK radius. And that's the other model where we assume the sudden release model. And again, we get something that complies with ice cube, and it can produce, 50% or maybe something like that of the GZK cosmic rays. Now, note that neither the neutrinos nor the cosmic rays can explain the observed cosmic rays at low energies. So a GRB model, an internal shock model, can only produce these very high energy cosmic rays. But it can do so without, even in the internal shock model, without affecting so without being constrained at the moment by ice cube. Of course, with the full array, the limits will go down, and then I think it will start impacting that. And that will just tell us that the internal shock model, even when you do it time-dependent, is not the correct one. That's my expectation. That we should be using a different model, for instance, a photospheric model. So, the ice cube upper limits actually do not yet constrain the internal shock model. And they don't constrain the ability of the internal shock model to provide a significant fraction of the 10 to the 19, 10 to the 20 electron volt cosmic rays. But these models should anyway not be the one to be used, so we should be looking at a better model. And of course, GRBs do not explain the lower energy sources, and as I mentioned, they cannot explain they won't explain. So as you can see, the Waxman-Bacall limit is somewhere here, and the neutrino spectrum is way below. So PeV neutrinos are way below the PeV neutrinos at ice cube as we can observe. Okay, so there was one very bright, very nearby burst that I mentioned, this guy here at the redshift 4.34. One would have hoped that there would be neutrino detections from that object. There was no neutrino detection. Is it surprising? I don't think so. We calculated the standard internal shock model neutrino flux, and we don't expect neutrinos from it. And even for one of the two photospheric models, we don't get a flux high enough that could have been detected. These are calculations by Shangao and Kazumi Kashiyama. And so in a model-independent calculation, we find that these are a radius where the neutrinos are produced, or the cosmic rays are accelerated, in these Lorentz factor. There is a fairly large range of bulk Lorentz factors and shock radii that is allowed. You disallow these regions here. These observing 1 muon or 10 muons, 5 muons, 2 muons, or 1 muon. So you can rule out these regions, but there is a substantial region that is allowed. And for the internal shock model, there is an even larger region that is allowed. So there is no constraint from the non-detection on either the internal shock model or a generic model. Now, a baryonic photosphere model produces a flux which is also unconstrained. the magnetic photosphere model, that's the one that is constrained. So there, the allowed region is very small, and so you would really say that the magnetic dynamic, the photospheric model where the dynamic is magnetic, can be ruled out by the non-detection of ice cube into burst. So again, ice cube is, after all, doing a significant contribution. So at least these models certainly ruled out. It hasn't ruled out the other two. So these saying words, what I just said. You do not constrain either the internal shock or the baryonic photosphere, but you do constrain the magnetic photosphere. And now, what about the population tree GRBs? What kind of neutrino fluxes do they produce? I mentioned before the photon fluxes. So you can do the same thing. You argue that there are photons produced by the photosphere, pair annihilation photosphere, and you have an external shock. So you have the photon spectra from the pair annihilation photosphere and from the external shock, and then you'll have, that's your target photon spectrum, and you'll have acceleration of cosmic rays at the external shock and at the photosphere, and they'll interact with these photons. And so these were the spectra. And now these are the neutrino spectra that you expect from various models. And I'm not going to go into details. It's calculations of Chantal in a different paper. So these are population tree bursts. So they are very massive bursts, and the burst lasts a whole day. So these are the neutrino fluence over one day for a black hole, which is a 300 solar mass black hole. So it's a very large type of black hole from a progenitor star that may be 1,000 solar masses, and an external density which is relatively large. So you get a flux which you could compare. So here's another comparison. For a lower mass black hole, let's say a progenitor star of 100 solar masses, you get fluxes which are below the ice cube limit, the 5-year limit, although these not a very exact calculation, because one would have to fold the sensitivity of the instrument with the specific spectrum, which we didn't do. But so you expect that you might detect these high mass population tree GRBs. You might detect the neutrinos from the high mass, very high mass GRBs, population tree GRBs, but not from the more moderate mass. And here's, so here's how the 300 solar mass GRBs compared to the ice cube 5-year limit, you would expect to detect them. Mind you, these at energies of these 10 to the 15 G, 10 to the 15 electron volt, these 10 to the 17. Ice cube is not all that sensitive at these energies. So really one should be looking at Ariana or Anita or things like that. So there is also a contribution from GZK, neutrinos, but Ariana or Ara, something like that, or Anita, could be testing these type of population tree GRBs. Okay, so briefly for GRBs, the outlook is that theoretical issues I mentioned are the same as we had for the when I discussed the gamma ray radiation. The TeV and GeV neutrinos would be a key ingredient, and they would tell us whether their hadronic contributions to the photon spectrum, whether protons are accelerated, etc. It would tell us about shock parameters and so on and so forth. Now there was a type of observation which is done by IceCube, and this was the first detection of what are almost certainly astrophysical neutrinos at PeV or sub-PeV energies. These are slides that I stole from Shoecraft. Initially, there were first two PeV events which were nicknamed after some comical characters, 1.1 PeV, 1 PeV. These how they looked in the strings, and so these are cascade events. They're obviously not muon neutrinos. And cascade events, they have very poor directionality, so it's very hard to tell where they come from. And then there were more events detected, initially 28 events. These are the 2 PeV events. The rest were somewhat sub-PeV, 100 PeV and all that. Some of them were muon neutrinos, the others were cascades. They are definitely above the atmospheric neutrino background, so the significance is 4.1 sigma. Including the high energy Ernie and Berti, significance is almost 5 sigma. So these published in Science, and being above atmospheric neutrino level, these are almost certainly astrophysical neutrinos. Are there any obvious sources? One can say that there are no obvious sources, just because there is poor directionality for the cascade events. The muon events, they don't point at anything particular so far. I mean, they continue to analyze it, but so far there is no significant evidence of any correlation. Now, could they be GRBs? And I mentioned to you that the diffuse flux from GRBs is just too little. It's not enough at PeV energies. So we may detect eventually the neutrinos from GRBs, but these flux is above that level that GRBs can provide. And certainly in time, they don't coincide with any observed GRB, even in the vague remote similar direction. So there is no time coincidence with any GRB, and no coincidence even with the rough, extremely rough position of any GRB. And the flux is not enough from GRB. So it's not GRBs. So what else could it be? I think that one good bet is that they might be hypernova. Hypernova are a small fraction of the supernova 1Cs. Maybe 3 to 5% of the supernova 1Cs are hypernova. Hypernova are, they are like the regular supernova, but they have a portion of the ejecta which is semi-relativistic. So V over C of order 1 for a smaller amount of mass. And the total kinetic energy then is more like 10 to the 52.5 ergs instead of being 10 to the 51 ergs, which is the typical kinetic energy of the supernova, and the typical ejection velocity is maybe 0.1 C. Okay, so these are, if you want, hyper-energetic supernova, but they're a smaller fraction of the total. And those that are close to the galactic center, we thought initially they might be the old egret unidentified sources, and that those might be hypernova. It's possible. But most of the observed PeV and sub-PeV events are away from the galactic plane, so it's unlikely that maybe there are 1 or 2 that are in our galaxy, and the rest have to be from somewhere else, way beyond the halo, probably cosmological. So I think they're predominantly isotropic, probably they're extragalactic hypernova. And one type of galaxy where you find a lot of hypernova is in the so-called ultraluminous infrared galaxies, or starburst galaxies. I mean, here had a paper arguing for that, although she got the flux which was a little bit below, so she was initially pessimistic about it. This is just a little plot of how supernova kinetic energies branch off. So down here for low mass stars, less than 20 or so, or 25 solar masses, you get the normal supernova with the neutron star remnant. And for higher mass progenitors, you get the black hole remnant. And you can get 2 classes of supernova. One is the very faint branch. Some of these are associated with GRB, and then there is the super-energetic hypernova. And a lot of these are not associated with GRBs. So in fact, these hypernova are much more frequent than GRBs. So that's another reason why we think that they are better candidates for being the source of these PV neutrinos. There are many more of them than. So now, could the hypernova be GZK cosmic ray sources, since they are semi-relativistic and very energetic? The answer is, if you compute what is the maximum energy to which such a semi-relativistic ejecta could accelerate cosmic rays, it's about 4 times 10 to the 18 times Z, the charge of the nucleus. So for protons, maybe you might get up to 10 to the 19 electron volts, but for iron, you could get to the GZK energies. So it could be that hypernova are also a possible source for ultra energy cosmic rays. More generically, one can argue that it's sources where proton-proton collisions occur, which are the source of the PV neutrinos. In a model-independent way, one can show that the spectrum would be, maybe e to the minus 2 or minus 2.2. And if so, the spectrum would be something like that. And you can show that from PP interactions, you would not violate either the Fermi gamma ray limits, and you would explain the ice cube observations with such a spectrum. So that's a generic argument. Specific PP scenarios, they could occur in radio galaxies. In the accretion disk, you can have PP collisions just from cloud collisions. And so, they have a high density enough. Or in cluster accretion shocks, you also have PP neutrinos. You can accelerate up to 100 PV cosmic rays, which would give you, 2 PV neutrinos. So these also could be sources of them. And then starburst galaxies, similarly, you produce supernova and hypernova, and isolated hypernova. So, these are possible specific candidates of these PV neutrinos produced in a PP scenario. And one interesting thing to note is that you could argue that all the cosmic rays from 10 to the 9 electron volts to 10 to the 21 maybe come from the same type of sources. That's because in all 3 energy ranges, you have more or less the same energy rate production. So in the low energy range, so there are 3 ranges: the low energy range, the medium energy range, and the high energy range. Low, medium, high. The high energy range, the energy production is 10 to the 44th megawatts per cube per year. The medium energy range that is being tested by these PV neutrinos also indicates the same energy density, the same energy production rate. And for the galactic cosmic rays, you can base it on the radio radiation or on the observed cosmic ray flux, and you get, within 1 order of magnitude, you get something very similar. So you could argue in principle that it looks like you could make a case that all these cosmic rays, all the way from 10 to the 9 to 10 to the 20, come from the same type of source. The problem is, of course, that this is a simple argument based on energetics and energy rates, but you don't know what these sources are. I was arguing that the ultra-energy cosmic rays can be GRBs. GRBs certainly don't do that, so these same type sources certainly not GRBs. It may be something else. All right, so the outlook for cosmic rays and neutrinos is that the sources are not yet known. We know that there are certainly astrophysical sources, they are not top-down sources. The photon production for top-down sources would have been too high. GRBs remain decent candidates for GZK cosmic rays, so do AGMs. And I think that GeV and TeV photon observation, so combining cosmic ray neutrino and high-energy photon observation is the way to constrain the type of sources. In particular, ultra-energy neutrinos are very important. as well as the diffuse gamma ray constraints. And the composition, determining the composition will have to be settled, but that will be a very important factor. Thank you very much.
Still have several minutes. Any questions? No, then I have one. Okay, the universe will become transparent to the gamma ray above the PV again. So some of the model here, are they producing the gamma ray above the PV?
Well, gamma rays above PV have not been detected so far, so that's one problem. But you expect the production of PV gamma rays in some objects. In gamma ray burst, it's difficult because you have gamma-gamma going into pairs. So typically the cutoff is at 10 TeV, the gamma ray burst. Hypernova and AGNs could be making PV photons, but then if they're at high redshift, the PV photons get killed by interaction with the CMB. So it's difficult to observe, but I think they're being produced, just there's no way to test it.
The other important tool is the neutron spectrum.
Yeah.
Okay. So are they producing some of the detectable signal?
Well, it's expected, that at the distances that they occur, the neutrons would decay into protons, and so they wouldn't arrive as neutrinos. I mean, from very nearby sources, within the GZK radius, maybe, but they would have to be extremely energetic ones. So I think that the direct neutron detection is probably not hopeful here.
The neutrino part,
Yeah.
beta decay
Yeah.
could be another signal.
Yeah, the beta decay signal is expected, and that will produce a weak halo of photons when the positrons then they annihilate and they produce gamma rays. So you get a little halo. It's a weak signal. It's an expected signal, but